Before we go to the free-falling droplet experiment to look at the droplet combustions experiments, we shall give you some examples to illustrate the droplet evaporation. There is another technique you may use, but those kinds of techniques usually is limited for the purely evaporation experiments. Okay, you look at the figures in the left-hand side. The experiment basically composed two heating plates, and those heating plates is provided by the electric power, and they will heat the region in between these two plates. Okay, and this is a very simple experiment, and we use a thermocouple, and those thermocouple is very tiny, and you can suspend it. You can have a droplet suspended just on the junction of your thermocouple, just like the picture show you. This is a time series pictures to tell you starting from the 0 second. There is the in this case we use water as an example. This is a spherical water perfectly attached to the junction of your thermocouple. Okay, and this thermocouple basically is a moving. Why we are moving this thermocouple? Because we need to heat the gaseous environment in the region between these two plates initially to a certain fixed temperature, and we use there is the fixed thermocouple to measure the temperature of the environment between these two plates. Then, as the temperature reach to prescribed temperature required for experiments, then we move the thermocouple with the droplets into the center of your test zone, test regions. Okay. Now we say the upper thermocouple is moving, and the lower thermocouple actually is fixed and used to measure the local temperature of the hot environment. Okay, now when you move your water droplet into the center of the heating regions, then you do the measurement with the dimensionalization. Here this is D divided by D naught. D naught represent the initial droplet size. Here we use the three different kinds of size of droplet, water droplet. One is the 1.34 millimeter, the other one is 54 millimeter. The other and the next will be 1.58 millimeter, and you can see the break symbols represent this data, and the open symbols represent the temperature of inside of the the droplets. Actually, they measure by the thermocouple junction, and the thermocouple junction is very close to liquid surface, but the temperature represents the interior temperature of your droplet as a reference. You can see from the data representation in this plot. Okay, and you find out actually all the data, even we move cold water into the heating zones, you can see very earlier there is almost do not have too much change for droplet size. As I mentioned, in reality, especially you will find out the droplet size is almost remain constant. Okay, that means that they may have a short time for preheating. But in this case, since the temperature for the surrounding one is the 310, and the other one is the 428, and the higher temperature will be the 506. Okay, and you figure out the environment temperature are different. Okay, then you can see for the square or the square symbol, actually the environment, the 310, has a lower temperature, which means that this supply heat is not efficient compared with the other two cases, 400 and 500, right? That means they do not have enough heat transfer for the preheating. Therefore, the preheating period will extend longer. But for the 400 and the 500 cases, then you can find out the preheating zone, preheating time is almost negligible. Okay, and in for these three cases, actually, I show you the droplet diameter is slightly different, but you can treat as the same size. The major influence will basically coming from the surrounding. Okay, we use 300, 400, and 500 different kinds of high temperature environment. Okay. Now you can see for these three droplets, three cases, actually the d square, the droplet surface change basically is a linearly decrease. Okay, this can be described very well by the d square law, and you can see there is the so-called slope here. This is a slope. This k. K is basically is described by the so-called evaporation rate constant by d square law. For comparing these three lines, you can see the droplet size actually droplet they are similar droplet size, but in the different hot environment, for the temperature in the hot environment is low. For this case, the droplet lifetime means then you can extend this square law to the finally at this point. That means the droplet size diminishes, disappear. Then this is a lifetime for the droplet. Okay, and a simple, very simple. Simply to see that the droplet lifetime for the droplet in the lower temperature is longer because they have a weak evaporation strength. But when you increase your surrounding temperature up to 500, you can see this line will reach to a smaller lifetimes because they have more heat supply for the droplet evaporation. And by the same thing, you can think about the slope. Okay, the slope, the K for the high temperature case is larger compared with the lower case. Okay, K is controlled by the spotting number. Spotting number tell you if you have a high temperature environment, then the heat transfer to your droplet is higher. Then the spotting number is stronger. You will have a K, larger K. Larger K, that means that your d squared 9 will has a sharp gradient, and the droplet will be complete disappear in a shorter time. Okay, this is a typical experiment to let you know in the purely evaporation process, the droplet size basically is well described by the d square law. Now we go to the combustion case followed by the the free falling droplet experiment. I think you can have these figures from the lecture notes, but I use slide to describe it as a more clearly. Okay, now you think about the structure is like this. There is the spherical droplet because we generate from the droplet generator, and then these strings go through the hot environment. In this hot environment, actually they are ignited and burn it in the hot environment. Okay. Now, in the experiments, we will measure the droplet size, but we use the non-dimensional quantity to represent the experiment data. The first one, we say this is a capital RS. Capital RS basically is defined by small rs divided by RS naught. RS represents the instant droplet radius, okay, and RS naught that represent the initial droplet size, droplet radius. And therefore, at any instance, the droplet radius will be non-dimensional by the initial size. Okay, then we call this as a capital R S squared. Okay, okay, this is a non-dimensional quantity I want to mention. Okay, the second one, there is the frame positions. We call this as a capital RF. Similarly, capital RF basically is by the real frame positions, frame radius divided by the the droplet radius at the initial time. Okay, and for RS, capital RS and the capital RF represents those kinds of non-dimensional quantity at any instance to tell you the droplet size change and also the frame size change. Okay, but for RF tilde, I need to explain a little bit. because RF2 that we already mentioned from the d square law formulation, this is just a comparison between two radius. One is the frame radius, the other one is the surface radius. Actually, they tell you basically they try to tell you the ratio between RF and RS representing the stand of a distance. That means that we are not looking at the size of the region between the liquid surface and the frame surface. Okay, and we want to see the how the change of these regions is become smaller or become larger, and this tell you some important physical informations we will explain later. And now we return to the d square law formulation. This is the equation for d square law. Originally, they used the diameter, right? But now we use a radius instead of the diameter. Then you need to have a 4 occurs in front of the rs to the power 2. And here this is 4 for the initial droplet minus kT. This K will be the so-called evaporation constant. Now, when you do the non-dimensionalization by Rs naught, then the left-hand side will give you the capital Rs square, capital Rs to the power 2, and then equal to 1 minus K. And here there is a time we bring those kinds of quantity together as a group, and T will divide by this group quantities. Then this will give you the non-dimensional time. Okay. Okay, you can see, I'm sorry, this is not a non-dimensional time, but this is simply tell you that they can represent the time because the Rs naught square, Rs naught is a constant from the beginnings, then this T represent the time only. Okay, and we try to bring these results from the experiment data and show by these figures. Okay, at first we look at the Rs square variation, this one, d square law, okay. The horizontal axis represent the time variation, and the vertical axis represent the variables we will discuss. The first one is Rs square, okay. You can see this is the solid dot points represent the d square, the R square, right? The radius square, that means the droplet surface. You can see there is the linear curve, okay, complete the same for the prediction from the d square law. And additionally, here in the first two points, dots represent the value, the R square equal to 1, represent the droplet size almost no change. In this time, actually refer to the so-called preheating, the droplet preheating in this case. In this case, we burnt this droplet strength in the air environment with the oxygens is 12.5 and the nitrogen 87.5. Okay. And I want to mention again here, since we try to do the the whole conditions more related to the ideal gas storage, then we use the in the whole temperature, the whole experience is under very low atmospheric pressures. Okay, and you can see actually when you use the low pressure environments, actually you reduce the buoyancy effect. Okay, in this experiment, since you just impinge the droplets along the droplet strings, and you do not supply the very strong flow convections, usually they always have the flow convection, but we try to minimize it, and we try to ignore the buoyancy effect. How to ignore the buoyancy effect? You try to reduce the density. Okay, you reduce it. Even you do the experiments in the on the Earth, then you still have a gravity, but you understand the buoyancy effect is coming from the density change times the gravity. You have a gravity, but the density is very small, then you will try to minimize the influence coming from the buoyancy effect. Okay, this is the thing I want to mention. And the liquid fuel basically is corresponding to the octane. Okay. And octane fuel. And now I just explained the variation of your droplet radius. Then we go to look at the capital RF and RF tilde. Okay, the capital RF here, capital RF is a square symbol, triangle symbol. Triangle symbol here to show you the frame position, right? Non-dimensional frame position. And the open circle represent the standoff distance between the liquid surface and frame surface. Now look at these two, the variation of these two value. The first one, you can think about the frame position actually in the period, in the initial period, okay? They have a slightly increase, then later on they will decrease. What happened about this kinds of expansion? Okay, initially you can think about it. When you have a droplet start to evaporate, the droplet size should be continuously reduced, right? It's a shrinkage because you let the liquid coming out from the liquid surface. But in this initial periods, droplet size is a slightly decreased, but frame increase. What's going on about the increased distance of your frame position? You remember the motion of your diffusion frame basically is controlled by the balance between the fuel supply, the fuel diffusion, and oxygen diffusion strengths, right? When the diffusion frame move away from the fuel side, that means the fuel supply stronger than the oxygen supply. Then they will push to the oxidizer side. Therefore, you understand in the initial region, since the droplet is relatively cold, and they just start to produce a vapor. When the vapor coming out, they do not have a when that vapor coming out, those kinds of vapor will accumulate in the vicinity of your liquid surface, but the frame initially is not too strong because the supply they're coming out, but they do not have a strong burning. Then those kinds of fuel will accumulate in the regions between the droplet surface and the frame. And this you can see, okay, we look at the RF tilde represented by open circle. There you can see they have some kinds of increase. That means the standoff ratio means the region between the liquid surface and the frame surface in continuous increase. Continuous increase means that those kinds of fuel vapor has a stronger concentration that push your region increase, and in the sense in the same time, the frame will be pushed to the oxidizer side. But when you have a more fuel coming out, that means the supply to the diffusion frame becomes stronger. Then the diffusion frame will become stronger. They have ability to overcome the additional fuel vapor coming out. In this sense, the fuel will start to balance with the supply of the frame will be balanced by the supply of the fuel. They can maintain at a constant burning rate. Okay, and here you can see the frame continues to be reduced, and this kind of reduced since it's caused by the droplet surface reduced in the evaporation process. In this region, while the frame will move away from the liquid surface, we call in this short periods, we have a lot of fuel vapor coming out. The frame will be pushed out, and which means you have more fuel vapor compared with oxygen should be diffused in. Then we call this a so-called the fuel vapor accumulation. Those kinds of accumulation will push your frame away from the liquid surface. Okay. But in this environment, actually, we can see the burning intensity is not too strong because oxygen is not too much, and this will tell you the burning of your diffusion frame basically is not too strong enough to finish all the fuel vapor coming out from the from the liquid surface. Okay, this is the motion variation of your flame surface and the liquid surface. Now I go back to let you know the other case for the burning for the pure oxygen region. Let me go to our slides, okay, and we start to give you some comparison, okay. Now we go to the page 2.7 here, and to show you the other set of experiments. Okay. Now you can see it's clearly in this second experiment we are working on the pure oxygen environment. Okay, and when you have a pure oxygen environment, then the burning intensity is very strong, right? Very, very strong. And you can see for the D square law, the R square actually the preheating zone, I'm sorry, not the preheating zone, preheating period is diminished, almost no preheating. Okay, which means that you have a large amount of heat transfer to the your liquid droplet, and the liquid droplet start to heat it up to the vapor temperature very fast. Okay, and you can see for the RF here, represent the flame position. Initially, they will push to far to closer to the oxygen very fast, but they will reduce, okay, continuous. And those kinds of tendency reduce flame radius is much stronger than the previous case. Okay, and the stop this is a smaller gradient, but this is large gradient, means the actually the when the initial pure vapor may accumulate certain amounts without burning, but later on when the flame temperature the diffusion flame becomes stronger, they will consume it very fast, and they will move to the closer to the droplet sites. This is one thing. The other thing is in this very efficient burning process, the droplets evaporate very fast, then the droplet surface reduce very fast. Okay, by these two effects, the standoff distance between the flame position and the liquid surface reduce very fast. Okay, and here they tell you, okay, in the final periods, actually the standoff distance almost fixed. Almost fixed means the flame move to the liquid surface, also liquid surface reduced, and this position is almost keep constant. By this way, that means that in these periods, the flame basically is do not change because when you based on the coordinate change, actually they tell you the diffusion from the fuel is balanced with the oxygen. Okay. And typically, if you consider these two cases, actually you can see from the D square line, this is a D square straight line. That, in this case, because we are burning in pure oxygen environment, the slope, okay, this slope is much larger than the slope in the previous case. Okay, and these two plots give you some comparisons for the burning in the less oxygen environment and a pure oxygen environment. Okay. Now I want to give to some conclusions to think about the spherical symmetric droplet burning. And from the previous formulation based on the D-square law, we try to simplify our problem. Therefore, you have some assumptions. We try to neglect the gravity, but in reality, actually, gravities will give you the buoyancy effect, especially accompanied with the big density difference near the diffusion flame. Usually, your flame will not retain as a spherical. Actually, it's destroyed, just like they will have a tail flames. Okay, and by this influence, because all the hot products will be pushed by natural gas upward, then the burning rate usually is increased. This is one thing I need to mention. The second one, as we learn from the experiments, there is the droplet heating you need to consider in the initial period for the droplet in the hot environment. That people will use the so-called diffusion limit or distillation limit to try to modify it, and it's very nicely to give you some corrections on droplet heating. But in general applications, actually droplet heating is only occurs in a short time. Usually you can neglect it, is you will not have too much differences. Okay. And I mentioned there is a few vapor accumulation before. They will change some frame position locations. And here now these two droplet interaction and a flow convection, where people look at these two subjects very seriously, because in real application we usually burn spray as a as a liquid type. Now, when you have a spray, that means that you have a lot of liquid droplets, and those droplets will interaction together. Okay, and so many papers published on droplet interactions, and also for the flow convections. Flow convection is a very important law to for even for single droplet combustions. And now I want to stop here. Maybe for the next times, I will give you the more understanding, especially for the flow convection, the influence of flow convection on the droplet burning.